There we go. Now there should be sound. Now there should be sound. Sound, sound, sound. Maybe it's too low, but okay. Sound now. Hopefully there should be sound. That's better. Excellent. Okay, great. I just had the audio setting not feeding from the microphone. Okay, cool. So, greetings RISC-V friends. So, today what I'm going to be trying to do is soldering up one of these boards. So, let me focus. Okay. There we go. So this is a testing board, and there is an Adafruit FTDI 232 board, which connects via USB, so you can control it from, say, a Python script. And basically it's just got either I2C output or SPI output or GPIO output, which is great. And then I've got these 4 chips, which are GPIO expanders. So they have 40 GPIOs each, and they will go ahead and manipulate and read all the pins on the backplane. So I can use this to test all sorts of boards. I have a backplane. Here's one that I've been soldering up. So this would fit like that. So, and then I would put, you know, some other board here, and then I would test it. So I need to, I'm off mic there. Okay, so I need to make 2 of these boards. I need to make 2 of these boards. Let's see if I can bump up the advanced audio properties. Let's see, mic. No, I can't even increase the microphone pickup. Well, that's fine, whatever. Maybe I'll talk a little louder. Okay, so I need to build 2 of these. First of all, because I can't actually test this unless I maybe solder onto the pins on the bottom. But what I'd rather do is build 2 of these and test them against each other. So that way I can at least sort of bit out of focus. Yeah, okay. That's because I don't have autofocus on. So, all right, so mainly I'll be working over here. So let's see. All right. So mainly I'll be working over here. I really wish that I could get, oh, you know what? Yeah, let me just pull up an app that may let me increase the microphone pickup. This is an app called Peter's Equalizer APO Configuration Extension. And hopefully I can go ahead and grab the microphone and maybe increase the preamplification. Sometimes it just doesn't work because it's, I guess, Windows, and, you know, Windows often says it's doing something and it never does. So, okay, well, I guess we're just going to have to live with this, and I'm going to have to be careful to keep the microphone next to my mouth. All right, so I also have this. So I have a camera on top of the microscope, which is kind of cool. So this is not the board that I'm going to be soldering. It's a different board, but it has a chip on it that has a pin pitch that is larger than the chips that I'm going to be soldering. This is, for example, the chip that I'm actually going to be soldering. This is the GPIO chip. So you can see that it's got a pin pitch of probably half. Yeah. So what I thought I would do is just solder this up. Now I have a Hakko FX951 soldering iron. Let's go ahead and switch to the camera. So this is the tip that I'm using. Well, I guess you can't really see the tip. Maybe I'll put it under the microscope. Maybe that'll work better. Okay, so this is the tip that I'm using. Yeah, you can't really see it very well. Yeah, sorry for my awful video setup, but I'm not a professional. Anyway, it looks like, let's do this. That's a little better. It looks like your ordinary chisel tip, but it actually isn't. There is a reservoir in there. So it's actually a concave chisel tip. I have a larger one here, which may be easier to see. It's kind of hard to see because it's three-dimensional, but yeah, there you go. So you can see that there's a little well in there. And I first heard of these from Dave at the EEV blog. And the idea is that you have a little well of solder in there. And as you solder your part and you drag this down like that, the solder sort of is drawn from the well. Now, I've seen a whole bunch of videos on drag soldering, and they all have a different technique. So I'm just going to try one technique. So you can see that I've already done two sides. I'm going to try the third one. And again, I'm sort of sorry. I'm not sort of sorry. I really am sorry about the terrible video quality that I'm getting out of my microscope. I do have another microscope on order. There's this channel called Strange Parts on YouTube. They just had a podcast on the amp hour. And I went over to their channel, and there's a microscope that they get from China, which seems to have some pretty good video quality, and it's fairly cheap, so I have that on order. So what I'm using here is I'm using flux, rosin flux. It's not the no clean version, so this is the toxic version, I guess. I don't know. And what I'm going to do is I'm going to take my soldering iron, and I have some thin solder here. I'm just going to fill up that well a little bit. Okay. And then I'm just going to place it flat side down and just sort of drag, see what happens. Okay, so there was some effect, and I was basically modifying the angle a little bit as I go by. But you can see that I've got most of them done, and they didn't really bridge either. So anyway, this is a pretty easy chip to solder. So there's not really much challenge. I mean, you could even do each individual pin one at a time. So that's not the challenge. The challenge is this board, which obviously has a much finer pin pitch. But let's get to one of the more interesting features on this board, which is this. Let's see if I can get it more in focus. So this is where the power supply goes. It's a DC to DC converter. So here is the place where I'm going to put the power jack. So for comparison, here's the other board. That's the power jack. And the power goes in, and there's an input capacitor here. And then there's this LGA, which is it's a 5x5 LGA, which stands for land grid something. What does the A stand for in BGA? Ball grid array, right? Land grid array. I don't know why I blanked on that. So it's a 5x5 land grid array, and most of the pins are actually connected to ground, with the exception of these 2 input pins and these 3 output pins. 2 of them are actually outputs, and one of them, I think it's maybe this one, is the feedback input. So that's what the chip or module uses to detect the voltage that it's outputting and adjust it based on the load, which is kind of cool. Anyway, the module itself is a few bucks. Let me see if I can grab it. Now the thing is, you can't hand solder this. So I'm going to be using some hot air. All right, so what I'm doing now is, let me switch cameras so you can see that I'm actually digging through a box. So I'm just looking for the okay, these are the jacks. I'm looking for the converter. These are LEDs, so I'm going to need all these. What's this? This is the I/O expander. I'm going to need that. Here we go. DC to DC converter. It's from Inoline, or Inoline. It basically takes anything from, I think, 3.6 volts or so to 17 volts, and it outputs 3.3 volts at 3 amps. The reason that I need such a large power supply, or such high current, is that when I plug in this tester board to the backplane, this really needs to power the entire backplane. So I figure 3 amps is probably nice. What PMIC is that? So the part number, so it's an Inoline. It's an RPM 3.3-3.0. It's from Recom Power. So I guess RPM is probably Recom Power Module, and 3.3 is the output voltage, and 3.0 is the current. You can get it on DigiKey, and I think it was only a few dollars. By few, I mean like less than 3. So anyway, this is the module. Let's go switch to the microscope view. Microscope view. All right, so this is the underside. It's basically just, this is just a printed circuit board on the bottom, and this is the module itself. So there we go, Recom RPM 3.3-30, and it even has the specs written on it. Input 3.3 to 17 volts, output 3.3, 3 amps. Okay. So the idea is that, I've looked at a bunch of videos, and it seems that what you do to solder an LGA, sorry, I'm letting my American accent slip through, and I'm trying not to do that because I don't want people outside the US wondering, why is he pronouncing it solder? That's a really weird pronunciation. So solder. So I've seen people basically just put some solder on the lands or the pads, and then put this on it, and then just apply a heat gun. Now, I guess you could use solder paste, but I'm just going to go ahead and put some ordinary solder on. So let's just go ahead and do that. Now, the thing about the pins that I'm soldering right now is that they're actually connected to the ground plane. So I do have to apply a fair bit of heat, but it does seem to be working okay. So yeah, it seems to be working okay. So I have my soldering iron set to 330 degrees Celsius, which seems to be working out pretty well. One of the dangers of setting the soldering iron at too high a heat is that when you get to pads, so when you get to pads that are as small as these, some of these pads aren't even connected to anything because they're no connects. And it's really easy on high heat to basically burn the adhesive between the pad and the printed circuit board, and then your pad lifts, and then you're screwed. And I've had that happen on the first board when I had my iron set to, I think, 450 Celsius. Luckily, I was able to repair it because the pad didn't completely come off. All right. So now I've got solder on all of the pads. So what I have to do, first of all, I always put a dot on the footprint. And you can see that there is a dot. Hang on. There. So there's a dot on the footprint, and you can see over here that there is a dot on the module. So, of course, that's how I align them. Basically like that. I guess I'll just do this by hand. So basically, it's going to sit just like this. So the next thing that I have to do is apply heat. So first of all, switching to the other camera now. All right, so I've got this neat stick. This is a stick vise, and anybody who solders any printed circuit board should have one. So I'm going to put this in the stick vise. And this just basically adds weight to the printed circuit board so that it doesn't move around so much. And I'm going to put it in the stick vise so that it sort of sticks out like that. I'm doing this at the wrong angle, so bear with me. All right, so I have it sticking out. That way I can sort of stick it out from the table like this and apply heat from the underneath. So I'm going to put the part onto the LGA in the right orientation. And I guess it doesn't have to be very exact because the surface tension should move the part itself into the right orientation and the right position. So now what I'm going to do is I'm going to attempt to take the camera and the heat gun and heat it up so hopefully you can see that the part will actually settle onto the pads. And then I'm going to test it and make sure that it actually made electrical connection. So let me grab my heat gun. Okay, here's my heat gun. So let me plug that in. Okay, so the plan is that I'm just going to heat this up. I don't think I don't think I want to heat this up from the top because that might blow the part away. I'm going to heat it up from the bottom, which is a little iffy because this is a 4-layer board. So the top layer and the bottom layer have traces, but the inner 2 layers are basically planes, power planes. So one is the ground plane and one is the power plane. And those actually need to heat up from the bottom, great, to the top. So it might take a little time and it might, you know, heat up the circuit board, but I don't have any other parts on here. This is the only part that I'm going to be doing this to. The front of it should. Oh, really? So, like this. I did not know that. Okay, well that's cool. So I learned something. So I'm going to try to be fairly careful with this and focus this on the part. Here, let me, okay, zoom in a bit. There. So you can definitely see that there's, oops, let me see if I can. All right, there we go. So you can see the solder blobs underneath there. So yeah, so an underboard heater. Yeah, I do actually have a chemical heat plate, hot plate. But I don't know. This seems to be good enough. All right, so I'm going to attempt to hold the camera here and then heat this up from the bottom. So let's see. All right, I think that's probably about as good as it's going to get. Going. Okay, I think that might have done it. Let me just visually check it. Yeah, it looks like the PCB that is attached to the module is now flat onto the PCB of my board. So, yeah, it looks pretty good. There's a few shiny spots. Why are there shiny spots? I don't know, but I'm going to test it. So let me put the, Okay, let me put the heat gun away. And let me put the camera back. Okay, so there we go. Let me get the heat gun out of the way because I don't need that. Right, so the first thing that I'm going to do is test it to make sure that there aren't any shorts. So I'm going to test the continuity between ground and input. And in theory, there should be none. Let me put it on diode, because there should also be a protective diode in here. Okay, so I'm measuring so with the positive lead on positive and the ground lead on ground, I'm measuring 2.9 volts. And if I swap the leads on the input, oh, that's not good. Oops. Oh, yeah. Okay, so the case is actually connected to ground, and I had the lead touching ground. There we go. So there is a protective diode of 0.5 volts. So that's good, and now let me check the output. So I'm going to connect the ground lead to ground, the positive lead to positive, and I get nothing. And if I swap the leads, I get another protective diode of 0.43 volts. Great. So I think this actually worked. The component syncing down to the PC was nicely observable. That's great. I'm glad that you could actually see that, because that really sort of hits home that, you know, the printed circuit board on the module just sort of presses down right onto the board. So that's cool. All right. So the next thing that I'm going to do is let me switch to the microscope view again. And focus. Great. Okay, so here is the input capacitor, C1. So the input capacitor, let me switch again. Switch. Okay, input capacitor. Oh, I took out all the parts already so that I wouldn't have to dig around. Okay, here's my parts. So I have an input capacitor. Now I'm using a non-polarized input capacitor. Let's see, these are 0.1s. These are resistors, so I don't need any more. GPIO, green LED, jack. Here we go. So I have a ceramic non-polarized capacitor of 22 microfarads, 10 volts, so that's the output capacitor. And this one is 10 microfarads at 25 volts. Also ceramic, also non-polarized. So I'm just going to stick that on. So let's switch back to the microscope. Yeah, this is Hassel. So this is hot air solder leveling. That basically means that I don't have any fancy coatings on it. It's just, you know, hot air solder. The printed circuit board was made by JLC PCB in China. Come on, microscope, microscope. There we go. So that's where I get all my printed circuit boards made up. I really like their quality. I've never really had a bad board from them, which is nice. So what I do is, so my strategy for soldering surface mount components like this is I first take the component. Okay, so there it is. So basically what I do is I apply solder to one pad, and then I heat up that pad, and I just sort of push the component onto it. And then I just solder the other pad. So that's what I'm going to do, except I'm going to do it with my other hand, like this. Where'd my solder go? Right here. So I'm using the same tip because I can't be bothered to change tips, but oh, you know what I should do? Apply flux. More flux. Flux is always good. Oh yeah, so the card edge connectors. Hazel is terrible for card edge connectors. You really should have it ENIG, E-N-I-G, coated or finished. Because with Hazel, when you insert and remove the card edge from the connectors, eventually that stuff is going to wear off. So, but this is just a prototype. So I don't really care that much. Obviously, for the final version, I'm going to have it ENIG coded. So here we go. All right, that's okay. Now the solder is a little bit sluggish because I've got a large heatsink area. You can see this whole thing is basically a heat sink. All right, so sometimes what I do is I just press down the component to make sure that it's flat. Right, and then I'm just going to... Oh, that was terrible. Yeah, the reason that it's going so terribly is because of this heatsink effect. So it doesn't work as well, this technique. Okay, great. So that's one side. And then I'll just flip it. First, let me alter my stick vise so that it's not sticking out anymore. Okay, there we go. All right, here's the other side. And now this is connected to the ground plane, so it's probably going to be even more sluggish. But that's okay. It's not like a very sensitive component. I think, is that it? It's hard to tell whether it actually there we go. Now we can see the solder sort of wick onto the pad. Okay, great. Is this out of focus again? Well, that's about the best focus you're going to see. Again, I've got another microscope coming in, which from the YouTube videos seem to be better. So, okay, so that's that. Let's do the output capacitor. So the output capacitor is 22 microfarads at 10 volts. Now, I designed this, yeah, that's right, JLC PCB, that's right. So I designed the printed circuit board in KiCad or KiCad, however you would like to pronounce it. All right, so here we go. Flux. And solder up one pad. And grab the capacitor. sure it's flat. And there we go. Very nicely placed. Now the other side. Good enough. Okay, so the final piece to this circuit, let's see, is that FPGA? No, I'm not putting a RISC-V processor on an FPGA. The whole point of this project is not to use an FPGA anywhere. So it's going to be discrete. There's a lot of boards and a lot of slots on the backplane, so it's a big project. Check the whole playlist. Let's see. Any other question? Is there some way of knowing your streaming times a little bit in advance? Well, okay. Generally, see, I thought that YouTube would actually announce to people who subscribe when the next live stream would be. I actually scheduled this 2 days ago for this time. And I also sent out a tweet. So, you know, I don't know. The platform doesn't seem to be working as expected. So, unfortunately, the answer is no. There really is no real way to get a guaranteed notification. Sorry. Just, you know, subscribe to me on Twitter. Check my Twitter feed. My Twitter should be in my info on YouTube. My profile info. If not, it is Babbage Boole, which I will type into the chat. Okay, and I didn't type it into the chat. There we go. So that is my Twitter feed. That's where pretty much I announce most things and where I also send pictures to on things that I'm doing. So that's kind of cool. All right. Where is, here we go. Okay, so I also put a power LED in there so that I could, you know, tell that power was actually on. So let's go ahead and hook that up. So let's see. The resistor is a 220 ohm resistor, which I sort of calculated on the back of an envelope based on, this is a 3.3 volt output, and the LED drops, you know, something like 2 volts. And it takes something like 10 milliamps. So anyway, so the markings on the resistor are 2, 2, 1, which means 2, 2, and 1, 0. So 220 ohms. Okay, there's flux. Let's see, which pad should I do first? How about this one? Okay, where did my solder go? For some reason that spool is always hiding. Okay, here we go. And I guess I may as well also do this pad while I'm at it. That's the more problematic pad because it's connected to the ground plane. So it soaks up heat. All right, where is the resistor? It's over here. I do kind of like to get the markings on the components facing the same way. True story. Way back when I was getting my first job, it was at a kind of a little cottage industry factory that was soldering together boards. And as a test, they gave me a board and said, okay, solder this up. Here is an example board. So I went ahead and did it. And of course, you know, I put all the transistors in the right way, the capacitors in the right way if they were electrolytic. But the resistors, of course, I said, you know, it doesn't matter. They're not polarized, so I put them in any which way. Anyway, when they went ahead and looked at my board, they said, oh, yeah, that's good, except we like to put the resistors in all facing the same way, so it looks nice. I got the job. Okay. So let's, great. Let's sneak in here and solder the other end. Okay. And now the LED. So with the LED, it's important to get it the right way. And there was supposed to be a marking on here. Let me see, do I have a blank board? No, I don't. Well, there was supposed to be a marking on this, on the footprint, showing which way the diode is supposed to go. Yeah, I know. 10 milliamps is a lot, especially with modern diodes. Yeah, when I grew up, 15 milliamps was the standard because you had those awful, huge red LEDs. I found that you could power them with as little as like 500 microamps now. But you know, I looked at the specs on this one, and it seemed to want 10 milliamps. So go figure. Okay, green LEDs. So anyway, as I was saying, there was supposed to be a marking on the footprint showing which way the LED goes. It's probably not strictly necessary, at least for me, because I know that this is the ground side or the negative side of the LED. So which side is the negative side? Here's the LED. That's upside down. Here's the LED from the side. And here's the LED from the top. So the question is, which way does it go? Well, what I usually do is I just take my multimeter and stick it on diode mode, and then see which way it lights up, because it actually does light up when you do that. So let's assume that I have this in the right way, and I'm going to try to focus a little more. Anyway. See, it lit up. So I have it the right way around, because this side is the negative side on my tester. Now, it's kind of hard to see in the video because the video is kind of low quality and all blurry, but you can actually look at the LED and see that there is a lot more metal on this side, and on this side there's just this thin wire. And when you look at the data sheet, the manufacturers will show a picture of how this is supposed to go. So, you know, you'll clearly see something. Now, it's also hard to see. Let me see if I can zoom in on this part and focus. There we go. All right, you can see a green line on this side right over there. So that green line is the negative end. So that's cool. Let's go ahead and solder that together. So now, yeah, the metal is on top, but you can sort of see that it also wraps around to the bottom there. So basically, all I have to do is melt this, and there we go. All right, let's solder up the other side. Solder. go. That's the power LED. So now in theory, I should be able to hook it up to power and see that the light lights up. Yeah, solder. I'm trying to get out of the habit of saying solder, as I said at the beginning of the video. I'm actually coming to dislike that pronunciation. I speak American English, and in American English, the word is pronounced solder, or sometimes solder, but I grew up pronouncing it like solder. And I'm trying to get out of that habit because I actually do like the solder pronunciation. Although I still insist on saying aluminum and not aluminium. Sorry. I like both pronunciations. Okay, what was I going to do? Oh, yeah. I am going to solder up this jack. Okay. Now, when it comes to power jacks, you need to be really, really careful about whether you're center positive or center negative. So you see that here's the jack, there's a center conductor and the outside conductor, and you need to decide whether it's going to be center positive or center negative. And I've looked online to see what's the most common, and the consensus seems to be center positive, unless you're dealing with audio equipment, in which case they go center negative. Go figure. I have no idea why. So that's the jack. Right, and of course, once you decide which should be, what polarity your center should be on your jack, you also need to choose the right adapter. And all the adapters that I got center positive. Yeah, I've heard that too, that aluminum is supposed to be the correct pronunciation. But, they say it, and that's proscriptive. But in terms of descriptive, it seems that most of the world has settled on aluminium. So, I don't know. Pronounce it however you like. It does seem, though, that a lot of people are offended at the American pronunciation of solder. So, lest I cause offense. All right. That's good enough. All right, let's take a look at the LED. See if I can get both things in focus. And now I'm going to plug in a 12-volt adapter. I have a 12-volt adapter here, but no plug that goes on the end. Where did I put my other adapter? Give me just 1 second. I don't know what I did with my other adapter. Okay, so I have an adapter, I just don't have the plug that goes to it. Why is that? Oh. I've got one. Let me make sure it's center. Let me make sure it's center positive. It is center positive. Great. That's good. All right. So let me plug it in. All right. The moment of truth. Smoke test. Yay! There we go. All right. That means that we have power. Great. So that's good to know. It means that the module is soldered together correctly. This is actually a 12 volt. Well, okay, so this can output 3 amps at 3.3 volts, which means that I would need 9 watts. So, you know, anything under an amp or approximately an amp should do. I just happened to find a 12 volt 2 amp supply. I have 12 volt 3 amp supplies, 12 volt 1 amp supplies, whatever, as long as the plug fits. Oh yeah, flux residuals. So I do have some IPA with me, 99.9% pure. So I could take some, and this isn't the best way to clean off toxic, the awful kind of flux, because it just sort of spreads it around. But it'll do for now. There we go. See, that sort of cleaned up a little better. That's nicer. I should do that all the time. Okay. Next. All right. Next. So I am first going to solder on the small parts, which are the capacitors here and the resistors here, and there's a bunch of other capacitors here. Also on the other side, I have a few capacitors that just wouldn't fit on the top side. I can leave those until later. So let me solder on the smaller components, which by now shouldn't be that interesting. So let's see, focus. That's about as good as it's going to get. All right, flux. Flux this, flux that, flux this in particular. Some resistors. This one has the capacitor on the other side. This one is on this side. There's some resistors here, pull-up resistors, and I think that's it on this side. So let's do the capacitors first. So these are just 0.1 microfarad reservoir capacitors. First, let me put away these other capacitors, these LEDs, into the right bag. Okay. And now I have these small dudes. These are 0603s. For these capacitors over here, these larger ones, I chose all sorts of different sizes. I chose 1210 over here, and I think this is an 0805, if I'm not mistaken. No, this is a 1206, and this is a 1210. Why did I want to make them big? I have no idea. This is an 0603. Oh no, this is an 0805. And this is an 0603. So I'm progressively getting smaller. Okay, let's take a look at the question. Is anybody else also annoyed by the mouse pointer in the center? Yeah, that is the mouse pointer of the camera itself. Let me see if I can move it. I just have to get a mouse. Here, let me plug a mouse in. Oops. Better? There you go. I aim to please. Okay. Oh yeah, Soul of a New Machine. Yes, I grew up on Soul of a New Machine. And that is sort of my inspiration here. Except I'm not doing wire wrap. Okay, so let's solder up one pad. There we go. Nicely placed. Solder up the other end. I guess I have to turn this. There we go. All right, let's see if we can quickly solder up the other ones. Then we can get to the interesting part, which is the chip itself. That's going to be the hard part. And that's going to be where the most failures will occur, which is always interesting. Success is not as interesting as failure. After all, when you watch a video of somebody doing a daring stunt, you really want to see what's going to happen. Let me see if I can change the yeah, this is just pretty much a horrible setup. So we're going to have to deal with it. Oh well. Okay, there we go. Okay, capacitor. Grab capacitor. Soldered. I'm just going to go through and put all the components on with the one side soldered. Uh-oh, I just lost my capacitor. I don't know where it went. They're pretty small. They are small. Okay. Let's see. I'll do the resistors after I do this one capacitor. All the resistors on this board, with the exception of the 220 ohm LED resistor, are all the same value. And that's usually a good idea, because then you don't have to worry about, oh, what's this resistor, what's that resistor. These are all the same value. All right, I think I got all the capacitors. Again, I'll solder their other sides later. So let me do these resistors now. Resistors, these resistors are 4.7K. I need 4 of them. 1, 2, 3, 4. You Can't ever really have too much flux. That's what they say. So this is 472. That's 47 with 2 zeros. Oh, come here. There we go. Now you're on the right side. So yeah, look at how sticky the flux is. I don't know. I don't think flux is all that harmful. I mean, if you breathe it in, sure. Or if you drink it. Notice, by the way, that I have no fume extractor. And I'll just leave it at that. You can argue about it as much as you like. Okay. These resistors now. Oh, is cleaning really necessary? Yeah, because flux does actually have an electrical effect, especially if you're dealing with fast speeds or sharp signal edges. It will act like a parasitic component. So you really do want to clean the flux off. For the most part, with most things, it's not really going to matter, but I would just clean it off, just as a matter of course. Just do it. Okay, so all the top components, all the top passives are on. Now I will solder down their other pads. Move this camera so that it's more straight relative to the board. All right. Did I do this one? I did do that one. This is where that reservoir in the tip comes in handy, because I don't have to keep applying solder. I might have to apply more here. Yeah, I think I ran out. Okay, there we go. All the passives are on. Now the fun part. Okay, so here is this really fine pitch component. It is a 56 TS SOP. So we've got this pad right over here is connected to ground. Then we've got this pad, which is VCC, and then we've got a whole bunch of signals. Signals, and some grounds interspersed. And, here we go. So if we look at these, they're actually not connected to anything. So applying heat for a long time to these pads is just going to lift them up. Now, again, they're not electrically connected to anything, so removing these pads isn't actually going to do anything. Nevertheless, I don't want to damage those pads. Here's another no connect. And if there's enough heat to lift one of these pads, then there's probably enough heat to lift, say, this pad, which just has one short little wire segment coming off of it. So let's zoom out a little bit and focus. There we go. So we can see there's my little dot that I put on the footprint. Okay, so first things first. I'm going to add flux. Oh, yeah, okay. So I've seen on some videos that they clean the pads beforehand with IPA. So I'm just going to do that. Can't hurt. All right. I think it's all dried up now. So now I'm going to apply some flux. And I've seen differing techniques. One where they position the chip, tack down the corner, and then put flux all over it. And some where they put flux first, and then tack down the corners, and then put flux all over that. It's just flux all over the place. All right, got my dot lined up with my dot. Now I just need to line the pins up. I do like to put the flux on first because it's a little bit tacky. Now these pads are, so these are the standard footprints in KiCad/KeyCAD, and I think they're probably meant for putting it in an oven with solder paste. This is definitely not for hand soldering. Okay, now I'm just going to gently press it down. Okay, now that I've pressed it down, I'm going to attempt to tack one side down. I'm absolutely convinced that professionals get a lot of knowledge from YouTube. You just cannot know it all. You can't. And YouTube is an awesome educational resource. Oh, I moved it down. Okay. Well, oh, you know what I should probably just do is put some solder in the reservoir and then just sort of, yeah. I mean, there's a solder bridge there, but that's okay. All right. So the next thing that I've seen, now again, I've seen people use chisel tips for this. But basically, and I'm going to rotate this board so that it matches the angle of my hand and my iron. But basically, they just sort of do this. I don't know, did that work? Probably not. Oh, you know what I forgot to do? I forgot to flux the legs. There we go. Flux, flux, flux. All right, let's try again. That definitely makes the solder flow a lot better. Solder. And I think I got all of the pins with the exception of these final ones, which are bridged. I'll deal with that later. Let's see if I can maybe zoom in and focus. Yeah. So, yeah, it's really, really hard to see because of the highlights. Let me see if I can remove some of the highlighting. That removed all of the lighting. Well, okay. I think this is actually good because you can definitely see the bridges now. So you can see the first 3 pins are bridged, and then these pins are actually soldered very nicely. I don't see any shininess between them. Now, what I've seen is that people are actually able to just touch the soldering iron to the bridge and have the solder wick up into the soldering iron. And that, oh, wow, look at that. I fixed one of the bridges. Let's see if I can fix the other bridge. I think there's too much. No, it doesn't look like I'm able to fix it very easily. Not sure why. Okay, I'll leave it there. Let me rotate this to get the other one. Okay, let's zoom out so we can see the whole chip. Chip, chip, chip. There we go. All right, so I will add just a little bit of solder. Solder. Okay, and now I will just drag it across. Sorry, I'm going to have to add more light so that I can see what I'm doing. It's going to blow out the video, but... Oh, flux. Darn it. Flux. Just pouring flux all over this really seems to make the solder flow very well. Very nice. Maybe that last pin. Okay. Let's turn off the light and see how I did. All right. You can definitely see bridges on the last 3 pins. The first 3 pins, rather. So let me go ahead and try to wick those off. Okay, got the first one off. See if I can get the last one off. I don't know why I can't just get these off. All right, well, let's use some desoldering braid. So I have some desoldering braid here. And what I like to do is put some flux on the desoldering braid itself. All right. Done. And let's do the other one. another bridge right here. And there's always a danger that you're going to take away too much solder. Done. All right. Let me just increase the light to make sure that it looks okay. I'm going to clean it with IPA. Yeah, I know. He really does drown the whole thing with flux, and I'm a fan. So, yeah. Yeah, the microscope's plane is not parallel to the tabletop. I did notice that, and I tried to adjust it, but I just couldn't very easily. All right. Okay. So I've noticed that there's another channel that I like to watch, My Mate Vince, and he admits that he's not an expert. I'm not an expert either. And what he does is he likes to sort of push on the pins to see if they move. And if they don't move, they're soldered down. Soldered down. Well, they're not moving. And I should check these ones here as well, because those are the ones that I use the desoldering braid on. And there's always a danger that you take away too much solder. Seems to work. And believe me, these pins are really delicate, and you can get them to move very easily. So just by applying a little bit of force, you can definitely tell whether they're properly soldered down. Okay, so that was that. So I could, of course, do the other three right now, but that would be boring. So what I'm going to do now is show the backplane. Now, I saw a comment about resistor networks for the win. Check that out, resistor networks. Here, let me focus that. Resistor networks and capacitor network. Okay, what is this chip? It's it's a GPIO expander. Let me actually type in the part number. It's an NXP PCA 9698 DGG. And it's I2C input. Now you'll notice that I had 4 chips on here. 1, 2, 3, 4. Oops, well, 4. Anyway, you can select the I2C address. I think you can select one of 16 addresses or something by connecting 3 input wires to either ground or VCC or the clock, believe it or not. Okay, so let me find my resistor networks. I hadn't actually planned on getting this far, so I didn't prepare that. So I'm just going to have to dig through my box, parts, to find my resistor and capacitor networks. which are not in my box. So that's weird. Let me just quickly look for them. Well, I have a bunch here. Let's see. I have... Okay, well, I've got let's see. I've got these. They're 100 ohms. That's the right value, but the wrong size, 2012. What's this? These are the capacitor networks. Ah, here, no, these are the resistor networks, 100 ohms. I think these are the right ones. Yeah. I may not have enough to finish this, but that's okay. All I want to do is a few. Yeah, so the vias, that is design variation. Some of them just got filled and some of them didn't, so. All right, let me just make sure that I'm using the right component here. So this was, wow, that's messy, oh my God. Holy cow. Let's try the other end of the board. Yeah, that's less messier. Okay, so you can see 101, that's 1, 0, and 1, 0, so that's 100 ohms. And then these capacitor networks, of course, you know, surface mount capacitors, unless they're electrolytic, usually don't have any markings whatsoever. These are the terminations for every signal on the board, on the backplane. And if you look on my channel, you will see a multi-part investigation into signal termination. And this is why I have termination, because it makes the signal edges cleaner. Okay, I put a resistor on this board and then turn the board around. Here it is. So that's the resistor right there. So let's go ahead and try to solder that up. Okay, so step 1, flux. Step 2, find the resistor. Where did I put it? I just set it down and, oh, here it is. So that goes like there somewhere. Okay. Now here what I think I can do is just hold it down with the tweezers. And the advantage of using this reservoir tip is that you can load it up with solder, and then you don't have to worry about having a third hand to hold the solder. So let me go ahead and add some. Okay. And I'll just take the tweezers and hold the component down. And then just, maybe I need to do it this way. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . It's not actually working. Maybe I need to load more in. Yeah, there we go. All right. And let's do the other end. Did I run out again? Oh, I think did I bridge? Let me turn off the light and see how that worked. I think there is a bridge in the middle. There we go. Perfect. Okay. All right, what about pre-tinning the pads before putting the part on? I've tried that, and the problem is that when you pre-tin the pads, they're not flat anymore, so the component doesn't lay flat on the pads. Because, you know, then you'd have to melt all of the pads at the same time. So, yeah. You pass too fast. Yeah, I might be passing too fast on the pads. That's certainly a correct observation. Okay, so what I wanted to do was look for the capacitor network, which I still can't seem to find unless, yeah, this is it. Okay, so the capacitors are 150 picofarads, and they look different from the resistors. Okay. So here are the capacitors. Let me see if I can get that in focus. There we go. Now, believe it or not, these capacitors, this capacitor network is not upside down. You can see on the side how the pad sort of wraps around. So this is, I think, the equivalent of QFN or FN, which is, or just N. N just means no leads, right? So that just goes on like that. Where's my flux? Flux. Okay, what I'm actually going to do, because okay, so for this, this doesn't have any leads, and the capacitors, the resistors did kind of sort of have leads, but you saw how kind of difficult it was. I have another tip. It's this chisel tip right here, which I've had actually some really good success with in terms of these types of components. So I'm just going to quickly change the tip, which I can do because I'm using a piece of cardboard to pull the completely hot tip off of this and not burn myself. And that's actually not working. Maybe I need to turn this off and wave the tip around a little bit. And then maybe I can grab it. No? Ow. Yeah, okay. I managed to pull it out. Okay, turn the tip back on, turn the iron on. All right, so now this thing is going to be heating up. So this kind of works the same way like a chisel tip, except you can see that it's sort of like a knife edge, in that you can put solder on it, like so. Let's see. Where's a good angle? None of these angles are very good, but that's okay. So you can just sort of put solder on it, like that. Oh wow, look at that, it's balling up. That's not great. Did I ruin my tip? Well, it seems to be working now. All right. So now that I have solder loaded up on my tip, I can place the component down and just hold it down like that and just run along it. Or not. Wow, that's really not working out very well. Holy cow, that worked out terribly. I don't know why it worked out so terribly. Wow. That was just absolutely, completely horrible. Let me try again. Maybe the tip just wasn't clean enough. Wow. All right, that's not working. All right. Well, the blade tip loses. Yes, I do have brass shavings. That's what I'm using. All right, let's just go ahead and remove that tip and try a different tip. I actually had good luck with this tip when I soldered up. Clean tip, flux, and don't go that fast. Well, okay, I'll try that. Cleaning the tip. All right, the tip is pretty clean and shiny now. Flux and don't go that fast. Okay, let's just add more flux. That's a lot of flux. Let's put the piece down and let's rub it in the flux. Oh, maybe I have to put flux on the part also. So, you know, like that. That way there's flux all over the place. Okay. Put the solder on the iron. Great. And solder it up. Slowly. I think that did it. Let me turn off the light and examine. Yeah, I think that looks good. I don't see any bridges. Now, the only way to really test it is the only way to really test it is to solder up the other end and then just test with a capacitance tester, which I'm going to do now. So let me go ahead and solder up the other side, applying a generous amount of flux, cleaning the tip very well, and oh, there's still solder on it. So okay, and just running along. Okay, I think that may have done it. So, okay, let me grab my capacitance meter now. And see what I'm getting. So, capacitance. All right, so between ground and this point, I am getting 0.5 nanofarads, or 500 picofarads. Now, okay, that's interesting. Without the probes connecting to anything, zoom in and show the fillet. I don't know if I can. Because the fillet is three-dimensional. That's about as good as I can do it. And, you know, you can't really see it. And I can't really tilt the board up like this and focus on it. Well, can I? Here, let's also turn the light on. See, you can't really see anything. There's something there, but, you know, it's kind of hard to see. And that back one doesn't look too good. Oh, that's not a back one. That is just the footprint. They do look kind of good. So again, what would also help is maybe cleaning the flux off. So let's just do that. Okay. And now, let's see what we get between here and here, or actually between here and here. Oh, now I'm getting an overload. Okay, well, I'm getting overload. Overload. What's wrong? Let me carefully touch on these leads. see. Here's 1. Here's ground. I don't know if I did this right. I'm not really getting anything. Okay, so here I'm measuring 0.46, so 460 picofarads. Here I'm measuring, well, it's moving around a lot. So it's not settling on any value. Here it's also not settling on any value. And here it's also not settling on any value. But, you know, it seems to fluctuate between 2.8 and 3.1 nanofarads. Same thing with this. Same thing with this. Not the same thing with this. So I think this may be not soldered in properly. Let's use a continuity meter. And see if I have any continuity. Well, let's see if I have 100 ohms here. Aha, I don't. So clearly this side is not connected to this trace. Luckily this trace actually doesn't go anywhere. This was an extra. Let's measure the other ones. 100 ohms. 100 ohms. 100 ohms. Good. Okay, so at least that means that the inner pads are soldered correctly, except for this one. And then I can always touch this pad to make sure that they're grounded. Right, so that means that these pads are connected correctly. So this one is the only one that isn't connected, and I don't really need to care about that. So, all right, that's good. So, all right, that is pretty good. What I want to do, I don't think I did this before, but I can take a capacitor and just measure it on its own. So let's move the capacitor into view. So there's the capacitor. Now, if I measure its capacitance, let's see what we get. Okay, so this is actually measuring at, oh, okay, you know what it is? All right, if I just leave these alone, right, I get 300 picofarads. Now, if I connect them up to the pads, I get 450 picofarads. Well, 450 minus 300 is 150 picofarads, which is how much this is. So I just need to zero this. Where's the zero button? I don't think there is a zero button. Ah, I can do relative. So now, all I have to do, now that I've zeroed it out, is touch these. Oops. And I get what it should be reading, which is, if I manage to get the probes in correctly, there we go. Oh. All right, well, it was reading about 160 picofarads, which is well within range. So now that I've zeroed out the probes, let's see what happens if I touch between the ground plane and here. getting nothing. How about between here and here? Okay, so now I'm getting 220 picofarads. So, okay. I just had to push this probe in a little more. And now I'm getting 220 picofarads. And now here, 220. And now here, also 220. And here, now I'm on the pad itself. 190, which, basically means that the capacitance being added by this trace and by this resistor and by these traces is not there. So, of course, if I connect up to here, I'm also getting 190 picofarads. That's interesting. What happens if I measure here? 220. Interesting. So is this actually connected? I think it actually is connected. Oh yeah, let me do the continuity reading again. Oh, maybe it is actually connected because I pressed this down. Well, they're all connected now. Well, alrighty. Okay, well, that's pretty much all I wanted to get accomplished today. So I think I'm going to end this live stream. So that was quite fun. So to review, we managed to solder up this neat LGA using hot air and these big capacitors, and we tested this LED, and then we soldered it in, and it worked great with the jack. So we know that that's working. I soldered in some of these passive components, and then we hit the chip, which really worked well with this chisel tip that has a reservoir in it. So that's cool. We learned that more flux is better. Flux makes things flow. That's what flux means. And we learned about these interesting components and how the reservoir tip really didn't help. And the chisel tip did sort of help, except you had to go really slowly and add flux to the component itself, because again, the component doesn't have leads that stick out to hold any flux remaining on the pads. So that was an important thing to learn. So that is pretty much about it. So again, let me switch to the other camera now. So there's the finished board with all components on. This is actually a separate module from Adafruit. This is the FTDI232H, I believe. It's called a USB GPIO chip, and it just plugs in to this board like that. And then you hook it up to USB. You can write Python programs to send I2C signals out to all these chips, which in turn will manipulate the GPIOs so that I can output signals and input signals and test things. And again, the whole idea is that I should be able to take a backplane like this, plug this in, plug one of these in. Here's the other one that we're working on. I should be able to plug another one of these in, connect one of these to power, connect a USB to this one and a USB to this one, and you can talk to both of them. And maybe send a signal through here and receive it through here, and make sure that all signals work. Once that's done, I can pull this out and give it to my friend who is working on testing scripts. why doesn't this want to come out? Okay. And he can use this to test other boards, and I can use this to test other boards that I plug into here. The next board that I'm going to be working on is the ALU, which can do addition, subtraction. It can do XOR, OR, and it can also compare. So those are important to some of the RISC-V instructions. So that's really the next step. So next step, finish this board, finish this backplane so that I can give it to my friend who's also helping me out with development, which is really cool. Probably finish this board. Solder up an ALU, or two of them, and give one of them to him, and wait for the test results to come back, and then continue on the voyage of building a RISC-V processor, not on an FPGA. So anyway, thanks very much for watching. I really appreciate all of your comments. They were very, very helpful, as always. I will see you on the next video. Bye.